All right, so this is the second part of this lesson on representing functions. And let's get straight into it. And I want to start with some terminology that's most likely new, although it's relatively simple. What it means if a function is either even or odd. And I will say that some functions are even, some functions are odd, a lot of functions are neither. So it's not like everything is either even or odd in terms of a function. So what does it mean if a function is even? If a function is even, well, in function notation, then f of x is always the same as f of negative x. Well, what does that mean? Well, think about transformations. The only difference, if you think about the the graph of f of x compared to f of negative x, is that f of negative x has a horizontal reflection. And yet, that should be the same as f of x. So if we understand transformations, we can think of this as meaning that a function is even if a horizontal reflection makes no difference. If the graph looks the exact same if you horizontally reflect it. Another way of looking at it is that means it is symmetrical around the y-axis. Right? For example, a simple parabola like x squared, if you reflect it horizontally, it looks the same. So f of x is the same as f of negative x. And any function that's like that, we say is even. Odd, a little bit more complex, if f of negative x is the same as negative f of x. It's odd. So what does that mean in terms of transformations? That means if you take a function and you reflect it horizontally, it'll look the same as if you reflect it vertically. And so an example of a function like that is x cubed. For example, here's x cubed. Okay. If I reflect it horizontally, it looks like this. If I reflect it vertically, it looks like what I just drew. So x cubed is an odd function. All right, so for each of these functions now, I think I have, how many do I have here? I have 4 functions here. For each, I want to state the domain, range, and then state whether it's even, odd, or neither. So first, domain. Let's look at this function here. We have a rational function. The domain is going to be everything except where we have a restriction on the denominator. So x cannot equal plus or minus 3. Again, a bit more obvious if I rewrite this as x squared minus 4 over x minus 3 times x plus 3. Right, and this relies on remembering about rational functions from pre-calculus 12. Anytime we're dividing by 0, we have either a vertical asymptote or a pointed discontinuity. Either way, that's the domain. And actually, I just realized I'm not asking for the range, so I won't worry about the range. Is this even, odd, or neither? So let's see. One way of telling is, let's see what f of negative x would equal. F of negative x would be negative x squared minus 4 over negative x squared minus 9. Right, everywhere there was an x up here, substitute it with negative x. And so let's clean this up a bit, and notice what I get is that's the same as just x squared minus 4, because a negative times a negative is positive, over x squared minus 9. And what I have right here is the same as what I have up here, which means f of x is the same as f of negative x. So without even visualizing the graph, I know this function must be even. And for all of these, I'm going to focus on them. Well, not for all necessarily, but for all these, I can focus on it this way. Again, it's not like you have to be able to visualize the graph. All right, so let's look at g of x. What's the domain? Well, it's a radical function. If I'm dealing with real numbers, x has to be greater than 0 or equal to 0. That's it. Is it even or odd? I know it actually must be neither, just because I can visualize. I know what this graph looks like roughly. I know this graph looks like root x, but with a horizontal compression by a scale factor of 1/2, but it looks something like that. Well, that function can't be even or odd because if I reflect it horizontally, it doesn't look the same. Reflected vertically, it looks like this. Either way, it's not this. If I reflect it in some way, it's not going to be the same as what we started with. And I could also go to my functions and I could replace x with negative x, and I see I won't get the same thing I started with. Either way, though, I know just from that this is neither. Neither even nor odd. All right, let's look at this function here, h of x, the cube root of 4x. So first, the domain. For this, you can find the cube root of a negative number, so the domain is all real numbers. Is this even or odd? Well, it kind of helps if you know roughly what a cube root function looks like, but I don't expect you to. So let's start with seeing if it's even. And see what h of negative x equals. H of negative x will equal the cube root of 4 times negative x. Clean this up a bit. We get the cube root of negative 4x, which is not the same as what we started. Right? These two are not the same. So it's definitely not even, because if it was even, these two equations should end up being perfectly equivalent. But they're not. All right? Let's see if it's odd. To see if it's odd, I need to check one more thing. I need to see what is negative h of x, which is pretty easy to figure out. I just got to go back to my original equation and put a negative in the front. Negative cube root of 4x. Right? Whole h of x with a negative in front of it. Now with that said, what may not be obvious right away is that these two are equivalent. And that's because the cube root of a negative number is, you can evaluate it. And so, for example, one way I can show this is if I take this equation up here and write it as the cube root of negative 1 times the cube root of 4x, using kind of what we know about radicals. Now again, the square root of negative 1 is not a real number, but the cube root of negative 1 is just negative 1. And so I can rewrite this now as negative 1 times the cube root of 4x, or just negative times the cube root of 4x. Notice these two are the same, which means h of negative x is the same as negative h of x. So therefore, this is an odd function. If you kind of know what a cube root function looks like when it's graphed, it looks something like this. They look something like that. It's my kind of lousy sketch. If you know that already, then you can bypass the algebraic, or can realize if I reflect this vertically or reflect it horizontally, I'll get the same image. Either way, it looks something like this. Oh, that was really bad. Let's try that again. There we go. Okay. With that said, we can't expect to know what all graphs look like in advance. And so let's look at this last function, I of x. First, let's find the domain. Now, this is pretty tricky because I got a radical inside a radical. So one thing I have to take into account is all of this right here. And that is that 3 minus root x, all of that has to be greater than or equal to 0. Which means 3 must be greater than or equal to root x. Or I could say root x must be less than or equal to 3. It's all the same thing. Okay? All that comes from what I have inside the radical. All right? Now as well, you may be wondering why I'm ignoring this part right here. Well, I'm not really ignoring it. I know if I look at that radical, I know right there that x must be greater than or equal to 0. I can see that quite quickly. However, again, I have a radical inside a radical. So if I look at the first radical, I can just see, okay, x has to be a positive number or 0, or x has to be a non-negative number. However, again, there's that second radical, and that's what I'm really focusing on. And so how do I solve this? Because that's root x must be less than or equal to 3. Well, what I could do is I could square both sides. And I get x is less than or equal to 9. But at the same time, up here, x also must be greater than or equal to 0. And so there's my domain. My domain is from 0 to 9. That's tough. And it's, I found the domain by inspection. And if you don't find that tough, be humble about it. Most students find that quite challenging. And I understand why. There's a lot of things to think about. That's it. That's my domain. So let me label that. If the domain is from 0 to 9, I don't care what the graph looks like. I know it can't be even or odd. Again, if it's even, it should look the same thing. It should look the exact same should I reflect it horizontally. But this graph doesn't even exist left of the y-axis. And so again, I know it can't be even or odd. So maybe I'll say one more thing. Let's say the graph looks like, I don't know, let's say it looks like this. Okay. Obviously, it can't be even, because if it was even, then it should look the same thing if I reflect it horizontally, but that's not the same. And if it's odd, it should look the same if I reflect it vertically or horizontally. With that said, I should label it, this is neither even nor odd. All right, so before I move on, keep in mind if something is even or odd, is actually, I think, quite simple to determine if you can visualize a graph. It's more difficult if you can't. All right, although before, I could also say, you can always come back to this, right? And if you still weren't sure about that last example, if it was even or odd, then do this. Substitute negative into x and see how it compares to the original function and whatnot. See if you really get the same thing or not. Next, I want to review piecewise functions, which I actually were introduced in a previous lesson, but really goes back to pre-calculus 11. Okay, that's it. A piecewise function is just a function defined in pieces. And what you see here are two pieces, although there's an extra blank right here that we'll get to. That's it. Let's sketch what we have here. So this piece, negative x plus 1, is a linear piece, but that part only exists. We only look at that piece when x is less than or equal to negative 2. So first, let's think what negative x plus 1 looks like. It's a linear function with a slope of negative 1 and a y-intercept of 1. So slope of negative 1, so it looks something like this. However, while I will draw this, I've drawn too much. What I want to show only exists, and I'm just trying to find a ruler right now, only exists from where x is less than negative 2. So from this point right here. So I want to sketch something like this. So that, what I'm highlighting in yellow, relates to that first piece. But those other points I drew, I'm going to erase. All right, so now let me look at the second piece. Now don't assume the pieces have to join up. They may not. The second piece is right here. 7 minus x squared, well, that's a parabola opening down with a vertex at 7. Again, for a moment, I'm going to ignore the restriction. And so I'm going to draw something up here. So the vertex is 7 up, and it's opening down. There's no stretch. So I know it goes to these points. I know it goes through these points. So it looks something like this over here. And then actually stops, because if I look at my restriction, it's from negative 2 to 0 only. So I'll draw it up to there, and I'll erase these dots over here. There we go. So what I've sketched out so far is what I gave you, the first two pieces. Then what I ask is to add one more piece, so that's an even function. Add at least one more piece, so that's an even function. Well, to make this an even function, I can, what I have here should look the same as if I reflect it horizontally. So right now, there's nothing on the right-hand side of the y-axis. But if it looked something like this, and then had a line going up like this, if that's what the whole function looked like, what I've just sketched out altogether is an even function. So what do I have to do to, what pieces do I have to add? Well, one thing I can do is I could either change the restriction on that second piece so that it goes from negative 2 to 2, or I can just add, which I'll do, I'll just add two pieces here. So one piece I'll add is, say, 7 minus x squared again, where from 0 to x to 2. Now, let me mention 0 here. Right now, 0 is not included in this function, so actually, to be honest, I should actually take that into account by showing an open circle right here. If you look at your restriction, try that again, make it a little darker. There we go. If you look at your restriction of that second piece, 0 is not included in that restriction. And so that's OK. I just have an open point there. Whereas negative 2 is actually part of the first piece. So that's why where those two pieces connect is a closed point. But right now, 0 is not actually included in the domain for that second piece, and so that's okay. I'll just leave it as an open point. And so what I've written down right here still doesn't include 0, but that's okay. It still will be an even function. That's it. I have that other line I have to draw as well. So I think, what's the equation of this line? It's probably easiest if I extend the dot slightly, and I realize that would be a line that has a slope of 1 and has a y-intercept of 1. So that's x plus 1. But only where x is greater than or equal to 2. So if I added those two pieces to right here, then I would have an even piecewise defined function. Okay, with that said, last question, I believe. Oh no, not the last question. The last question for this part is same idea, but I want it to be an odd function. So for that, let me go back up here and let me kind of erase this for a moment and think, what would this look like if it was odd? Well, that means if I reflect it horizontally, it should look the same as if reflected vertically, which means it would have to look something like this. You'd have to start down here. And then go like this. So if you visualize what I have here, notice if I reflect this horizontally, this whole thing now, if I reflect the whole thing horizontally, when I'm drawing in red, that piece would look like that piece would look like that, if I reflected the whole thing horizontally. What if I reflect the whole thing vertically? Well, that piece would come down here, and this piece would come up here. It would be the same thing I just sketched out. So again, what I've sketched out now, including what I gave you and what I just sketched out, all together, this is now an odd function. And so I just got to add these two pieces here. And so what are the equations of those two pieces? Well, the first part is a quadratic function with a vertex at -7 opening up. So the equation for that would be -7 plus x squared, or x squared minus x minus 7. And that's from 0 to x to 2. And that second piece at the bottom, that linear function, if I continue it a bit, I can see it's a linear function with a slope of -1 and a y-intercept of -1. So negative x take away 1. And again, that's where x is greater than or equal to 2. So before I move on, just keep in mind, and I'll leave this visual here, the visual you have here is the graph of these pieces and these pieces. Oh, it doesn't want to let me draw. There we go. All those four together. All those four together create the graph I have up here, and that graph up there is even. Oh, can't speak. Is odd. Sorry, as if you haven't noticed, I tend to say the wrong words a lot. Helpful, isn't it? That's it. Let's look at the last question. I have a right triangle, so I'm going to put the right angle, draw the right angle in here. A right triangle, it has a base of 9. Well, I can see that right here. Okay, the base length is 9. Express the area of the triangle as a function of its hypotenuse. Okay, area is a function of x. So in function notation, I want this. I want a as a function of x. That's what we're trying to figure out. All right, how do we find the area of a triangle? Well, area is base times height divided by 2. So area equals base times height divided by 2. Or in this case, it's 9 times h divided by 2. With that said, this is area as a function of height. That's what I have right now. What I've just written down is area as a function of height. I want area as a function of x as the hypotenuse. So I'm not done. Again, what I have written down right now is area as a function of height. A is a function of h. So how do I do this? Well, I have to find some way to connect the height of this triangle to the hypotenuse of the triangle. Perhaps not surprisingly, I'm going to use the Pythagorean theorem for that, because I can say that h squared plus 9 squared equals x squared. Now, what do I want to do with this? Well, I want to solve for h, because if I solve for h, I can rewrite the height in terms of x. So if I solve for h, that's quite nice to do. I can see h squared must equal x squared minus 81, which means h must equal the square root of x squared minus 81. Now, you may be tempted to put plus or minus, which is great, until you realize height is a distance. Distance must be positive. So I have that. And so the height of this triangle is always going to be the same as the square root of x squared minus 81. So notice if I go back to my equation right here, I have 9 times the square root of x squared minus 81 all over 2. And notice what I have now is an equation just in terms of x. So this is a as a function of x. This is what I'm looking for. And most likely, that's a challenging question. First is understanding what this means exactly. And again, this sort of way it's been written, express area as a function of x, that goes back to grade 8 and 9. I'm not saying it's easy, but that idea of knowing that in that order, that means x is the independent variable, a is the dependent variable. That has been the same sort of way we've been describing functions for years now. And so we do have to pay attention to that detail. Again, the wording is key. Because again, I could ask you to find x as a function of a, but that's not what I'm asking. Okay, that would be the inverse of this. That's it. What's the domain of this function? If I look here, I mean, I could do a few things. I could analyze the equation right here, and like we did in a previous question, to think about what values of x make sense so that, I can actually evaluate this. Or I can just look at the image I have right here and realize that the height of this triangle, so the hypotenuse is the domain. The height is also changing, but the domain of a of x has to do with x, which is a hypotenuse. And what is the hypotenuse? By definition, the hypotenuse is the longest side of a right triangle. So I don't even have to look at this equation here to know the domain. I could, but I think this is easier to look right here. And if I look at this right triangle, I can just see there's no way x can be less than 9, or there's no way x can equal 9. If x is actually equal to 9, this wouldn't be a right triangle. It would actually just be, well, it wouldn't be even a triangle if these two lengths were the exact same. It would definitely, and you had a right angle there. You would actually just have two lines on top of each other. That's the only way the x and 9 can be the same. But even that doesn't even make sense. So x has to be more than 9. Anything more than 9, then this triangle is possible. It's not possible to have a right triangle if x is 9 or less. So therefore the domain must be, x must be greater than 9. That's it. You can get the same thing if you analyze this equation here. But again, I'm not saying anything I'm doing here is easy, but I think it's easier to just remember what a hypotenuse means. And hypotenuse, by definition, is the longest side in a right triangle. So I don't have to look at the equation. I can know that x must be more than 9. That's it. Is it even, odd, or neither? Well, it might look like it's even. What do I mean by that? Well, let's see. Here's a of x. I have it kind of circled up there in orange. Let's see what a of negative x would be. OK? And what I'm going to do, it's going to maybe look like this is an even function. A of negative x would be 9 times the square root of, I want to have the exact same order I have here, yeah, negative x squared minus 81 all over 2. Right, I took function a of x up there, substitute the x with negative x. And if I clean this up a bit, I get 9 times the square root, negative x squared, the same as just x squared, minus 81 over 2. So it looks like it's even. And I'll even write this down. It looks even, but it's not. Why not? Because of the domain. This function only exists when x is greater than 9. And I've already kind of mentioned from before, if we have a function that only exists on one side of the y-axis, if it only exists on, in this case, where x is greater than 9, it can't be an even function. It can't be an odd function. It has to be neither. So I'll say it looks even, but by inspecting the domain, a of x is neither. But that's it. Chances are you find some of this challenging. I hope you do. That's kind of the point. But I'm gonna stop here.